Hello everyone, welcome back to the AIacademy's course on Python for data science. We hope you've practiced enough Python to feel comfortable with programming by now. Our goal is to show you how Python can be a powerful tool for tackling real-world data analytics and data science problems. We'll dive into two case studies, one focused on classification and the other on function approximation or regression. In this lecture, we will introduce the classification problem you'll be solving. Later, we'll dive into the data and solution in another lesson. Let us first discuss about the problem. Imagine a company, Grant Incorporated, which provides subsidies to individuals based on their income. Different income levels qualify for different grants. But when new people come in, it can be tricky to determine their income. So, let's leverage an existing database where personal income has been disclosed along with various attributes. The link to data set is given in the description section. The goal is to see if we can classify income levels based on these attributes. Specifically, we want to classify individuals with an income above or below $50,000. This is a classic classification problem where we'll determine whether someone earns more or less than $50,000. With this knowledge, we can estimate the proportion of customers in each income bracket and plan resource allocation accordingly. Another use case to consider is identifying potential outliers. For instance, if someone claims to earn less than $50,000 but their attributes strongly suggest their income should be above that, our classifier can flag those cases for further investigation. This helps ensure subsidies are allocated correctly, preventing misuse of these programs. So, let's get started. As with any data science problem, everything starts with data. For this case study, we'll be working with a dataset containing information on 31,978 individuals, including their personal income. This data will form the basis for building our classifier. Let's dive into the dataset and start developing our solution. Now, let's break down the features we're working with in this case study. There are 12 features plus one target variable, personal income, giving us a total of 13 variables. The dataset includes information on 31,978 individuals, so imagine a matrix with 31,978 rows and 13 columns. Let's quickly cover the variables and their descriptions to help you visualize the data before diving into the case study. The variable job type is a string that indicates the sector the person works in, such as federal government, local government, private, or one of 5 other job types. The education variable is also a string that tells you the level of education, which could be 10th grade, master's, doctorate, or one of 13 other possible levels. The marital status describes the marital status, such as divorced, never married, and so forth. The occupation indicates the type of work the individual performs, like armed forces, sales, tech support, or one of 11 other categories. The relationship variable tells us the individual's relationship to their household, which could be husband, wife, and so on. As you can see, each of these variables plays a crucial role because income is influenced by factors like the industry you work in, your education level, your occupation, and other personal attributes. Moving forward, you'll start to recognize which data is relevant for solving this problem. Let's take a closer look at the remaining features, which reveal more about an individual's demographics and financial situation. Race identifies the race of the person, such as black, white, or one of 3 other groups. Gender indicates whether the individual is male or female. Capital gain a rounded integer showing the capital gains made by the person. Capital loss another integer representing the person's capital losses. Hours per week an integer indicating how many hours per week the person works. Native country specifies the country of origin, such as the United States, Cambodia, or Canada. Salary status the target variable, categorizing individuals into 2 groups, those earning less than or equal to $50,000, and those earning more than $50,000. With these features, we're tackling a binary classification problem where we aim to build a model that can classify new customers into one of these 2 salary groups based on their attributes. However, gathering information like capital gains and capital losses might not always be straightforward. So, once we've built an initial classifier using these 12 features, we'll try reducing the number of variables to see if we can maintain accuracy with fewer variables. This would simplify future data collection efforts while keeping the model useful and practical. When you're approaching a data science problem, it's crucial to think through a structured process. Here's a quick overview to help you map your solution in Python for data science. First, define the problem. The first step is understanding the problem statement. In this case, we already know it. Can we predict an individual's salary status based on their attributes? If someone simply handed you the data and asked what you could do with it, a good problem statement could be identifying the salary status based on features like job type, education level, or marital status. There could be other useful questions to explore, but we'll stick to this classification problem for now. Next, we explore the data. Sometimes, you'll need to define problem statements from a large, loosely defined dataset. Our current dataset contains about 30,000 entries, which is moderate in size, and we're dealing with a straightforward binary classification problem. But in larger studies, you may need to break down a vague problem into smaller, well-defined subproblems before you can classify, approximate, or analyze anything. And then we move on to identify smaller subproblems. Identify these subproblems as distinct problem types, like classification, function approximation, or clustering. In this case, we're working on a binary classification problem with two classes, making the approach relatively clear. By keeping these principles in mind, we can follow a logical path to build a solution. Each step will become clearer as we progress through data exploration and model building. So, after breaking down those smaller subproblems, the next step is to arrange them into a logical solution that tackles the overarching, loosely framed problem. This is where the real intellectual challenge of data science comes into play. However, in our introductory course, the classification problem is straightforward, so conceptualizing it as a binary classification problem was simple enough. Now, we just need to figure out which tool is best to solve it. There are many tools available for classification, but the trick is knowing which one to choose. You can guide this decision logically by considering assumptions about your data distributions and the types of models that would work best. So, while the problem may seem simple on the surface, the underlying analysis and decision-making about tools and models is where data science really shines. The journey from problem definition to selecting the right tool makes it easier to develop an effective, meaningful solution. When choosing a tool, it's essential to base your selection on relevant assumptions and then test whether it works effectively. This step requires a bit more advanced data science thinking. For this course, we'll focus on a couple of tools, apply them to our dataset, and evaluate their effectiveness through prediction errors, confusion matrices, and other relevant metrics. After identifying the right methods, we will implement the solution on our platform of choice. Python and R are the most popular options, but we'll use Python here to tackle this problem. Once the solution is implemented and you're satisfied with the results, you'll have successfully completed the data analytics strategy and methodology. Alright, let's break it down a bit. As we discussed earlier, the problem itself is straightforward. We're developing an income classifier for individuals. But we've also added another layer to this problem that may not be obvious at first glance. We could use all the features to build the model, but we'd also like to explore whether we can reduce the number of features while maintaining similar classifier performance. Why is this important? In practice, having a solution that requires every single feature might limit its future application. But if we can narrow down the list to the most essential features while still achieving accurate predictions, we can make the system far more practical. A streamlined, focused set of inputs makes the classifier simpler, easier to implement, and ultimately more useful. So, this added challenge is a unique twist to the problem. As I mentioned, we've got a dataset with 13 columns. 1 is the outcome variable and the remaining 12 are our independent or input variables. Among these, 4 are numerical while the other 9 are categorical. Our task is to solve a binary classification problem that's also supervised since we already have the known outcome for every sample in the dataset. Our goal is to guide the learning algorithm to identify these known patterns in the data, which means we're supervising the learning process. The dependent variable is categorical and binary, while the independent variables include both numerical and categorical data. We will focus on reducing the number of input variables required to solve the problem efficiently. Our approach involves finding which features can be minimized without sacrificing predictive power, ultimately simplifying and improving the model. Alright, let's lay out the steps for our process. We start with our dataset and proceed to build a supervised classification model. But it's crucial to validate the model on test data after we've built it. This leads us to a fundamental concept in data science and analytics. If you use all the available data to build your model, it's likely to perform well because it's already seen everything. But that doesn't necessarily mean it will do well with new data it hasn't encountered before. The real value in data science comes from accurately predicting outcomes with new and incoming data. To estimate how well our model will perform on fresh data, we split our dataset into 2 groups, training data and test data. We build the model using the training data and then validate it against the test data we've set aside. This helps us gauge how well the model can generalize to unseen samples and gives us confidence in its predictive power. If our model performs well on the test data it hasn't seen before, we can confidently say that it should continue to work well in the future too. That's why we validate our model on the test data. Once we're satisfied with the model's performance on the test set, we can analyze the relative importance of our input variables. Let's say we have 12 variables available to predict salary status. Which of them plays the biggest role in determining the salary? What if we had to pick only 2 or 3? By ordering these variables in terms of importance, we can determine which subset of variables is enough to predict whether a person's salary is less than, equal to, or greater than $50,000. If adding more variables doesn't significantly improve the model's accuracy on the test set, then we know we've found the right number to work with. This step is essential because it ensures our model remains practical and usable. Reducing the number of input variables makes data collection easier and allows us to focus on the most relevant data. You'll find Python code and exercises to guide you through each of these steps, helping you apply what you've learned in Python so far. The first step is ensuring the data is clean. This means checking that the data aligns with expectations for each variable. For instance, if you're expecting a string, you shouldn't see a number in its place. So, consistency checks should be done to confirm that the data matches our understanding. During this process, you might discover missing data. For instance, not all individuals might have disclosed all 12 features. As a result, there could be rows with some missing values. Handling this properly is crucial to maintaining the quality and reliability of your analysis. For instance, some people might not have disclosed their capital gains or losses, leaving those fields blank. These rows represent samples with missing data, so what do we do about them? There are 2 common approaches. One option is to remove all rows with missing values. This approach avoids introducing artificiality into the data, ensuring accuracy. However, the downside is that you lose valuable information from other fields in those rows. If only one feature is missing, you're still throwing away data from the remaining 11 features in that row. Alternatively, you can fill in missing values using statistical techniques or assumptions. The benefit is that you retain the full dataset, but the downside is that you introduce some artificiality. The accuracy of these assumptions is crucial because if they're off, the imputed values may not reflect the true data. Choosing between these approaches depends on the proportion of missing data and the overall context of your analysis. Evaluate carefully to strike the right balance between data integrity and dataset completeness. After addressing missing data, the next step is to analyze descriptive statistics to identify which variables have the greatest impact on salary status and to detect internal relationships among the input variables. Here's the process. Identifying key variables. Some variables significantly influenced salary status. For instance, certain educational levels or job types could be strong indicators. We'll analyze the data to see which variables play a pivotal role in determining salary. Checking for redundancy. Look out for variables that are strongly correlated. For instance, if two categorical variables are consistently aligned, when one takes a particular value, the other also takes a corresponding value, including both in the analysis might be redundant. In those cases, consider combining or choosing one to streamline your classifier. Model refinement. After identifying and reducing the number of variables, build a classification model to predict an individual's salary status. A model with fewer but relevant features will improve efficiency and usability. Use case applications. This classifier helps plan subsidy allocation and monitor potential misuse. It gives a more rational and targeted approach to resource management. Using logical reasoning and understanding the underlying data distributions are crucial for selecting suitable tools and techniques for this classification problem. If you're not sure about the best technique for your data problem, a practical approach is to apply a range of algorithms and choose the one that performs best. Here's a step-by-step outline. Prepare a list of algorithms. Compile a list of common binary classification techniques, such as logistic regression, decision trees, support vector machines, k-nearest neighbors, and random forests. Apply multiple techniques. Train each model on the training data, using the same data split and preprocessing steps for consistency. This approach allows you to directly compare their performance. Evaluate with performance metrics. Assess the models using appropriate metrics like accuracy, precision, recall, F1 score, or ROCUC, depending on your specific needs. Select the best model. Pick the technique that yields the best performance based on your chosen metrics. It's a practical way to harness data science without needing to delve deeply into each algorithm. Refine the model. Once the best performing model is identified, refine it through hyperparameter tuning or feature selection to further enhance its predictive ability. This approach helps circumvent uncertainty about the best algorithm, letting you use the most effective one based on real-world data outcomes. The potential downside of trying multiple techniques without a clear understanding of the data can lead to biased results, especially if your dataset isn't representative. Here's how this can happen and what you can do to mitigate the risk. Bias in sampling. If your dataset isn't representative, certain techniques may perform well on it but falter on new, unseen data. Understanding data before technique selection. It's crucial to thoroughly analyze your data before selecting the algorithms. Look for any biases in sampling, data quality issues, and understand the relationships between features. Combine techniques with domain knowledge. Use your domain knowledge to assess the suitability of each technique. Not all algorithms handle biases and imbalanced data well, so knowing your data will guide better selection. Cross-validation and testing. To alleviate overfitting and bias, cross-validate your models by splitting the dataset multiple times and testing performance. Evaluate on fresh test data to ensure robustness. Evaluate model robustness. Analyze your chosen model's performance across different test scenarios, such as subsets of the data or different data distributions, to verify its consistency. By integrating a thoughtful approach with Python, you'll cover all these bases and ultimately implement a robust classification solution. Stay tuned for the next lecture, where we'll continue our journey through our course Python for Data Science. So, in upcoming lectures we'll guide you through using Python for data loading, feature engineering, model training, and evaluation to complete your data science project successfully. We hope that you have found this course informative and interesting. Please hit the like button and subscribe to our channel and stay tuned for upcoming courses. Your support means a lot and motivates us to create more educational resources for you. Thank you for watching and see you again in our next lecture.